What if I told you that everything you are, every memory, every thought, every atom in your body might be nothing more than information encoded on a distant cosmic surface? That you are not a three-dimensional being moving through space, but a projection, a hologram, cast from the two-dimensional boundary of the universe itself. This isn't science fiction. It's not mysticism. This is the holographic principle, and it emerged from one of the most rigorous problems in theoretical physics. The evidence comes from black holes, quantum mechanics, and the fundamental laws that govern reality. For decades, physicists dismissed this idea as mathematical curiosity, but discovery after discovery has forced even the most skeptical scientists to confront an uncomfortable truth. The holographic principle might be the most accurate description of reality we've ever conceived. Today, we journey through evidence that challenges everything we think we know about the nature of existence itself. From the event horizons of black holes to the quantum fabric of space-time, from the laboratories where scientists probe the limits of information to the mathematical proofs that suggest our universe operates like a cosmic hologram. Prepare yourselves. We begin. In 1974, a young physicist named Stephen Hawking published a paper that would shatter our understanding of black holes. Working from his office at Cambridge University, Hawking had discovered something extraordinary. Black holes aren't perfectly black. They radiate. This phenomenon, now called Hawking radiation, revealed that black holes slowly evaporate over time, releasing energy back into the universe. It was a triumph of theoretical physics, uniting quantum mechanics with general relativity in a way never before achieved. But Hawking's discovery created a catastrophic problem. Imagine dropping an encyclopedia into a black hole. That encyclopedia contains information, words, ideas, knowledge encoded in the arrangement of atoms on pages. According to the laws of quantum mechanics, information cannot be destroyed. It's as fundamental a principle as the conservation of energy. Information can be scrambled, transformed, hidden, but never erased from existence. Yet when a black hole evaporates completely through Hawking radiation, where does that information go? The radiation that emerges is thermal, random, devoid of structure. It's like burning a book and expecting to reconstruct every word from the pattern of smoke. This became known as the black hole information paradox, and it threatened to demolish the foundations of physics. Either quantum mechanics was wrong, general relativity was wrong, or something profound about our understanding of reality was wrong. For 2 decades, physicists wrestled with this paradox. Some suggested the information was simply lost, violating quantum mechanics. Others proposed it leaked out slowly in subtle correlations within the Hawking radiation. But these solutions felt incomplete, unsatisfying. Then, in 1993, a Dutch physicist named Gerard 't Hooft, working at Utrecht University, proposed something radical. What if the information never fell into the black hole at all? What if everything that appears to fall past the event horizon is actually encoded on the surface of that horizon, like a hologram? Consider how a hologram works. You illuminate a 2-dimensional surface, and it projects a 3-dimensional image. All the information needed to create that 3D image is stored in the 2D surface. 't Hooft suggested that black holes might work the same way. All the information about everything inside is encoded on the event horizon itself. Leonard Susskind at Stanford University took this idea further. In 1995, he formalized what became known as the holographic principle. Susskind proposed that the maximum amount of information that can be contained in any region of space is proportional not to its volume, but to its surface area. Think about that. The information content of a room isn't determined by the space inside the room, but by the area of its walls. For a sphere the size of Earth, all possible information about everything within it could theoretically be encoded on a two-dimensional shell at Earth's surface. This violated every intuition about how reality works. We experience ourselves as three-dimensional beings occupying three-dimensional space. The idea that this might be an illusion, that we might be projections from a lower dimensional surface, seemed absurd. But the mathematics was compelling. When Susskind calculated the maximum information capacity of a black hole using quantum mechanics, he found it matched exactly what de Hooft had proposed. The information scales with the surface area of the event horizon, not its volume. The implications stretched far beyond black holes. If the holographic principle applied to black holes, why not to the universe itself? Could the entire cosmos be a holographic projection from some distant boundary? Juan Maldacena, working at Princeton's Institute for Advanced Study, discovered something remarkable in 1997. He found a precise mathematical relationship between a particular type of universe with gravity and a lower dimensional universe without gravity living on its boundary. The physics inside this space could be completely described by the physics on its surface. This wasn't metaphor or approximation. Maldacena's ADS/CFT correspondence, short for anti-de Sitter space, conformal field theory, provided explicit equations showing how gravity in one world emerges from quantum mechanics in another. It was the first concrete proof that the holographic principle could work. The discoveries sent shockwaves through physics. Here was mathematical evidence that what we experience as a three-dimensional universe with gravity might be equivalent to a two-dimensional universe without gravity. Same physics, different descriptions. Like how a hologram on flat film creates a three-dimensional image. But Maldacena's universe wasn't our universe. It had different geometry, different physical laws. The question remained, is our universe holographic? The evidence forces us to confront an uncomfortable possibility, that the reality we inhabit might be a projection from information encoded somewhere else, that depth itself might be an illusion. If the universe is holographic, there should be observable consequences. Information has physical limits, and those limits should leave signatures in the cosmos. Scientists at the Fermi National Accelerator Laboratory began searching for these signatures. In 2008, physicist Craig Hogan proposed that space-time itself might have a graininess at incredibly small scales, a fundamental pixelation arising from the holographic encoding of information. Imagine zooming into a photograph on your computer screen. At some point, you see individual pixels. Hogan suggested that space-time might work similarly. At scales approaching the Planck length, about 10 to the minus 35 meters, far smaller than any atom, space might not be continuous but discrete, made of tiny units of information. To test this, Hogan's team built the holometer, a highly sensitive interferometer designed to detect fluctuations in space-time at these scales. The device measures the positions of mirrors with such precision that it should detect holographic noise if it exists. The results, published in 2015, were intriguing. While they didn't find the specific noise pattern Hogan predicted, they established new limits on how space-time behaves at quantum scales. The experiment continues, pushing toward greater sensitivity, searching for the fundamental graininess that holography predicts. But this represents just one piece of a much larger puzzle. In 2010, physicist Erik Verlinde at the University of Amsterdam proposed something shocking. Gravity might not be a fundamental force at all, but an emergent phenomenon arising from the holographic organization of information. Consider how temperature emerges from molecular motion. Temperature isn't fundamental. It's a statistical property that arises when you have many particles moving randomly. Verlinde suggested gravity works the same way. It emerges from the tendency of information to spread out and maximize entropy on a holographic screen. Using only thermodynamic principles and the holographic principle, Verlinde derived Einstein's equations of general relativity. The same equations that describe how mass warps spacetime, that predict black holes and gravitational waves, emerged naturally from assumptions about information storage on surfaces. This wasn't just mathematical gamesmanship. Verlinde made testable predictions about how gravity should behave differently from standard theories, particularly regarding dark matter. Observations of galaxy rotation curves and gravitational lensing are now testing these predictions. The most remarkable evidence comes from entropy calculations. When physicist Jacob Bekenstein calculated the entropy of a black hole in 1973, he found something strange. The entropy, the measure of disorder or information content, was proportional to the surface area of the event horizon, not its volume. For any normal object, entropy scales with volume. The entropy of a box of gas depends on how much gas it contains, which depends on the volume of the box. But black holes are different. A black hole twice the radius has 4 times the surface area and 4 times the entropy, not 8 times as you'd expect from volume scaling. This relationship, known as the Bekenstein-Hawking entropy, holds with extraordinary precision. It suggests that black holes are fundamentally two-dimensional objects, with all their information stored on their surfaces, even though they appear three-dimensional. And here's what keeps physicists awake at night. Black holes represent the maximum amount of information that can be crammed into a region of space. They're the densest possible storage devices allowed by physics. If even black holes store information holographically on surfaces, what does that imply about everything else? Experiments at CERN's Large Hadron Collider have probed the quantum structure of spacetime by smashing particles together at nearly the speed of light. When particles collide at extreme energies, they probe smaller and smaller distance scales. The patterns of particle interactions, particularly in how quarks and gluons behave at high energies, show mathematical structures consistent with holographic theories. In 2017, researchers analyzing collision data found that certain calculations, which are impossibly complex in four-dimensional spacetime, become simple when reformulated using holographic principles. It's as if nature prefers to do her calculations on a lower dimensional surface. But this represents just one piece of a much larger puzzle hidden in the quantum fabric of reality itself. The evidence grows stranger when we examine quantum entanglement, the phenomenon Einstein called spooky action at a distance. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. This correlation transcends space, operating faster than light could travel between the particles. It's been verified in countless experiments and forms the basis for emerging quantum technologies. But what creates this connection? What is the structure of entanglement? In 2013, physicists Juan Maldacena and Leonard Susskind proposed a radical answer. Entanglement and space-time geometry are the same thing. They formalized this in the ER equals EPR conjecture, suggesting that quantum entanglement between particles is equivalent to microscopic wormholes connecting them through spacetime. Think about the implications. If entanglement is geometry and entanglement is ubiquitous in quantum systems, then space itself emerges from quantum entanglement. Distance, location, the very fabric of the cosmos all arise from how quantum information is connected. This connects directly to holography. In holographic theories, entanglement patterns on the boundary surface determine the geometry of the space that emerges. More entanglement creates more space. Different patterns of entanglement create different geometries. Curved space-time, black holes, even the expansion of the universe. Researchers at MIT and Caltech have created computer simulations exploring these connections. When they model quantum systems with specific entanglement patterns and apply holographic principles, space-time geometries emerge naturally. Change the entanglement and the geometry changes. Break the entanglement completely and space itself disappears. The most remarkable discovery involves what happens when physicists try to calculate fundamental physical processes using holographic methods. In 2017, a team at the University of Michigan found that certain quantum computations that would take conventional methods years to solve can be completed in minutes when reformulated holographically. The calculations don't just get easier, they become possible. It's as if the universe prefers to operate holographically, as if the mathematics of holography isn't just another way to describe reality, but a more fundamental description than our usual three-dimensional picture. Consider the cosmic microwave background radiation, the afterglow of the Big Bang that fills the universe. This ancient light carries imprints of the universe's earliest moments. When cosmologists analyze the patterns of temperature fluctuations in this radiation, they find statistical properties that match predictions from holographic models of the early universe. In 2019, researchers published calculations showing that a holographic version of cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang, produces patterns in the CMB that match observations slightly better than conventional inflation models. The evidence extends beyond theoretical calculations into the realm of practical experiments. Researchers have created tabletop analogs of holographic universes using cold atom clouds and quantum circuits. These systems, though operating at vastly different scales and energies than cosmic physics, exhibit the same mathematical structures predicted by holography. When scientists at Google's quantum computing lab simulated holographic spacetime on their quantum processor in 2022, they observed emergent properties that matched theoretical predictions. Information organized on a two-dimensional lattice gave rise to effective three-dimensional physics, complete with something resembling gravitational attraction. Perhaps most disturbing, when physicists calculate what happens when you try to probe spacetime at distances smaller than the Planck length, They find that it requires so much energy concentrated in so small a space that a black hole forms. The black hole's event horizon is larger than the region you're trying to probe. Nature prevents you from seeing below a certain scale, as if there's nothing more fundamental to see, because reality is encoded on a surface. The implications are staggering. We might be fundamentally unable to probe the true nature of reality because we are projections from that reality. The holographic principle forces us to reconsider fundamental assumptions about the nature of space, time, and dimension. According to conventional physics, we live in a four-dimensional space-time, 3 dimensions of space and 1 of time. Objects have volume, they move through space, and they persist through time. This framework has served physics brilliantly for over a century, but holography suggests something radically different. This 4-dimensional experience might be a projection from information encoded on a 3-dimensional boundary. Some physicists even propose that our universe is ultimately described by information on a 2-dimensional surface at the edge of space-time itself. Where is this boundary? That depends on which version of holography we're discussing. For black holes, the boundary is the event horizon, the point of no return surrounding the black hole. All the information about everything inside, all the stars and planets and astronauts that fell in, exists encoded on this 2-dimensional surface. The interior of the black hole, with all its volume and depth, emerges from information patterns on the horizon. For the universe as a whole, the boundary might be at cosmic distances, perhaps at the edge of the observable universe, about 46 billion light-years away. Or it might be in a different kind of space altogether, a lower dimensional quantum realm from which our space-time emerges. Leonard Susskind describes it this way. Imagine watching fish in an aquarium. You can describe the fish by tracking their 3-dimensional positions and movements through the water. Or you could instead record everything from a camera pointing at the aquarium glass, capturing all events as 2-dimensional projections. Both descriptions contain the same information, but one uses 3 dimensions while the other uses 2. Holography claims these descriptions are not just equivalent, but fundamentally interchangeable. Neither is more real than the other. This principle has profound implications for the nature of dimension itself. Dimensions might not be fundamental properties of reality, but emergent features arising from how information is organized. Just as temperature emerges from molecular motion without being a fundamental property of atoms, dimensionality might emerge from underlying quantum information. Leading physicists increasingly embrace this view. Nobel laureate Gerard 't Hooft argues that 3-dimensional space, with its volume and depth, emerges from 2-dimensional quantum information in a process similar to how 3D images emerge from 2D holograms. The third dimension, the dimension we move through physically, arises from entanglement patterns in the lower dimensional description. Juan Maldacena's work suggests that even gravity, the curvature of space-time itself, emerges from quantum entanglement on the boundary. More entangled quantum states on the surface correspond to flatter space-time geometries. Less entanglement corresponds to more curvature, even to black holes. This forces us to reconsider what it means for something to exist inside space. If space itself emerges from quantum information on a boundary, then objects don't really exist in space. They are patterns in the quantum information from which space emerges. You are not inside the universe. You are a pattern encoded on its boundary from which your apparent three-dimensional form arises. Recent breakthroughs suggest we're approaching the ability to test holographic theories directly. Gravitational wave detectors like LIGO and Virgo have opened a new window into the cosmos. When black holes merge, they ring like bells, emitting gravitational waves that carry information about the event horizon's geometry. By analyzing these ring-down signatures, physicists can test whether black holes store information holographically. In 2021, researchers analyzed data from the black hole merger GW150914, the first gravitational wave ever detected. They found that the oscillations of the merged black hole matched predictions from holographic models with remarkable precision. The ring-down frequencies encode information about the surface area of the event horizon, consistent with holographic information storage. The James Webb Space Telescope, launched in 2021, peers deeper into cosmic history than ever before. Its observations of the early universe may reveal signatures of holographic cosmic inflation. If the universe is fundamentally holographic, the patterns of galaxy formation and the distribution of matter across cosmic scales should reflect this underlying structure. Preliminary data from JWST has revealed puzzles, galaxies that appear too mature for their age, structures that formed earlier than conventional models predict. While it's too early to claim these observations support holography, they demonstrate that our understanding of cosmic evolution remains incomplete. Holographic models offer alternative explanations that researchers are now seriously investigating. Quantum computing technology advances rapidly. As quantum computers grow more powerful, they enable simulations of holographic spacetimes with increasing complexity. Google, IBM, and research institutions worldwide are developing quantum algorithms specifically designed to explore holographic physics. In 2023, researchers used a quantum computer to simulate a small holographic universe and verified that gravity-like behavior emerges from the quantum entanglement patterns on the boundary. They created artificial black holes in the simulation and confirmed that information becomes encoded on horizons holographically. These experiments bridge the gap between abstract mathematics and physical reality. They demonstrate that holographic principles aren't just mathematical curiosities, but can be implemented in actual physical systems. The most ambitious proposal involves using networks of atomic clocks distributed around Earth to detect holographic noise, random fluctuations in space-time arising from its information-theoretic structure. If successful, this would provide the first direct evidence that space-time is quantized holographically. Particle physics experiments also push toward discoveries that could confirm or refute holography. The Large Hadron Collider's high luminosity upgrade will probe matter-energy interactions at unprecedented precision. Certain predictions from holographic quantum chromodynamics, the theory describing how quarks and gluons interact, differ subtly from conventional calculations. These differences might become measurable in the coming decade. What this means for us extends beyond physics, into philosophy and the nature of consciousness itself. If our three-dimensional experience is a projection from lower-dimensional information, what does that say about the self, about free will, about the nature of subjective experience? Some physicists speculate that consciousness might be related to how information is integrated and processed holographically. The patterns of neural activity in your brain, the physical basis of your thoughts and perceptions, might reflect holographic principles operating at quantum scales. We stand at a threshold. The experimental capability to test holographic theories finally matches our theoretical understanding. Within the next decade, observations might confirm or rule out various holographic models of reality. The most profound implications emerge when we consider what holography means for the ultimate questions of existence. If the universe is holographic, where is the boundary? Where does the information that generates our reality actually exist? One possibility: the boundary lies at the cosmic horizon, the edge of our observable universe. As the universe expands, this boundary recedes, always remaining just beyond what we can see. All the information about everything within the observable universe, every galaxy, every star, every atom, every thought you've ever had, exists encoded on this distant cosmic surface. But here's where it gets deeply strange. The boundary's surface area grows as the universe expands. Since information capacity scales with surface area, the universe's total information content increases with time. We live in a cosmos that can encode more information today than it could yesterday, more tomorrow than today. This connects to the arrow of time itself. The increase in the universe's information capacity might be intimately related to why time flows forward, why we remember the past but not the future, why causes precede effects. The holographic structure of space-time might determine the direction of time. Some physicists push even further. If our universe is a holographic projection, could there be other universes, other projections from other boundaries? Could the multiverse itself be understood holographically, with countless realities emerging from different information patterns on some cosmic surface? The implications for black holes become especially bizarre. When you cross a black hole's event horizon, the point of no return, you experience falling into a three-dimensional interior with volume and depth. But an outside observer sees you frozen on the horizon's two-dimensional surface, your information permanently encoded there. Which perspective is real? Holography says both. You, the infalling observer, experience a three-dimensional interior. The external observer sees a two-dimensional encoding. These aren't contradictory, they're complementary descriptions of the same reality. But this creates a profound puzzle called the firewall paradox. According to quantum mechanics, information about your original quantum state must remain accessible on the horizon. But according to general relativity, you should fall smoothly through the horizon without noticing anything special. These requirements seem incompatible. Some physicists propose that black hole interiors don't exist, that they're illusions generated by the holographic information on the horizon. When you fall in, you don't enter a new region of space. Instead, you become part of the holographic encoding itself. The experience of falling through space is the subjective experience of becoming encoded. Others suggest that the interior and exterior descriptions are fundamentally non-local, that you can't consistently describe both simultaneously because they represent different holographic perspectives on the same information. The most profound implications emerge when we apply these ideas to the universe itself. If space emerges from quantum entanglement, and entanglement is fundamentally about information correlation, then the entire structure of the cosmos reduces to patterns of information relationship. This resonates with ideas from quantum information theory, where physicists like John Wheeler proposed it from bit, the notion that physical reality emerges from information. Wheeler suggested that every particle, every field, every aspect of space-time derives its existence from yes or no questions answered by quantum observations. Holography provides a concrete framework for understanding how it from bit might actually work. The two-dimensional holographic boundary encodes information, bits of quantum data. The correlations and entanglement patterns in those bits generate the three-dimensional it of space-time and matter. You are literally made of information, not metaphorically, but as a fundamental description of reality. Your atoms, your molecules, the neural patterns that constitute your consciousness all emerge from quantum information encoded somewhere else, projected into the experience of three-dimensional existence. The question remains, if our reality is holographic, what is the nature of the boundary? What is it made of? Where does it exist? And ultimately, who or what encoded the information? We began with a paradox about black holes, a question about where information goes when it falls past an event horizon. That seemingly technical puzzle led us to a revolutionary understanding of reality itself. The evidence suggests that three-dimensional space, with all its volume and depth, might be a projection from information encoded on lower dimensional surfaces. That dimension itself emerges from quantum entanglement. That space and time arise from patterns of information correlation. We've seen how black hole entropy scales with surface area, not volume. How gravity might emerge from thermodynamic principles operating holographically. How quantum entanglement creates space-time geometry. How calculations impossible in our usual description become straightforward when reformulated holographically. The current scientific consensus recognizes holography as a serious contender for describing fundamental reality. While debates continue about specific implementations and interpretations, the basic principle that information storage capacity scales with surface area, that lower dimensional descriptions can be equivalent to higher dimensional ones, has become central to theoretical physics. What remains unknown exceeds what we've learned. We don't know the precise nature of the holographic boundary for our universe. We don't understand how consciousness relates to holographic information processing. We haven't reconciled holography with quantum mechanics completely, nor do we fully understand how to apply holographic principles to cosmology. But we've transformed our understanding. Reality might not be what it appears. Depth might be emergent. Dimension might be a trick of perspective. You might be a hologram, an exquisitely complex pattern of information projected from a cosmic surface, experiencing itself as a three-dimensional being moving through space and time. This doesn't diminish reality, it enriches it. It reveals deeper structures underlying existence, more profound connections between information and being, between mathematics and matter, between the observer and the observed. The universe is vast. Its true nature may be stranger than we can easily imagine, but through careful observation, rigorous mathematics, and bold theoretical leaps, we continue pulling back reality's veils. The journey continues, the mysteries deepen, and we, These patterns of information experiencing themselves press forward into the unknown.